All right, so let's talk about some other applications of orthogonal flows. So if you recall, we earlier discussed the idea of isospectral flows. So which have the following form. You have that y prime is equal to some function b, which maps a matrix, it's like to a skew symmetric matrix, y minus y by. You can write this as the matrix commutator of by times y, by and y. All right, so and if you recall, it's like you could show that the solutions could be written in the following form, right? So you can end up considering solutions of the form. Let's see, y of t is equal to q of t y0 q of t inverse. Okay, and in particular, it's like that allows you to rewrite this differential equation into an equation which q has to satisfy. Then q of t satisfies the following equation, that q prime is equal to b q y0 q inverse times q. But of course, as I said, it's like B is a skew symmetric matrix, so q prime is equal to b q b times q has the form, it's like of an orthogonal flow. And I guess I should have said that q is orthogonal, right? Q is an OD. All right, so the bottom line, if you will, is that if you use a method where the, if you recall, it's like if you had a Runge-Kutta method whose famous M matrix is identically 0, then it preserves all quadratic invariants. And since you can view the preservation of the orthogonality condition as being a set of basically something almost like half d squared quadratic invariants, it's like then those kind of Runge-Kutta methods will automatically preserve the orthogonality condition, and you could then use it, it's like to solve this equation for q, and then back substitute to get a discretization, it's like for the isospectral flow. Okay, so that's one possible application of orthogonal flows. All right, so let's look at another one, and the other one is basically going to be on the two-sphere. It's going to be on the unit sphere. And again, if you're thinking of the rotation group as a Lie group, then this application, it's like of orthogonal flows to flows on the two-sphere have to do with the fact that the two-sphere is a homogeneous space. Okay, so what that basically means is that there is a transitive Lie group action, or to put it more precisely, if you have a point on the two-sphere, you can get to any other point on the two-sphere with an appropriate rotation. Okay, so if you consider the orbit, if you will, it's like of the rotation action on any point, it's like then you get the entire two-sphere. So that basically means that the two-sphere is a single orbit of this rotation action. So what that basically means then is that if you have some curve, it's like what you want to stay on the two-sphere, then there's a sense in which you could rewrite that curve as some rotation matrix acting on some initial condition. So it's a little bit similar to this kind of ansatz, where you write the solution, it's like in some space, as some orthogonal matrix acting in some way, it's like on the initial data. And so you might imagine something similar happening here, it's like for the two-sphere. Okay, so the application then is to the two-sphere. Right, so this is denoted S2, right? This is the set of, say, x in R3 with the condition that the norm of x is just 1, right? Okay, all right. If you had, maybe I should call it y, right? If you had some little y, it's like which was on the 2-sphere, it's like then you can check that the equation which it satisfies is going to be of the form y prime is equal to a ty cross product y, right? Where a is some sort of 3 vector, where a is in R3. Okay, all right. So you have this A matrix, this A vector acting by the cross product on y. Okay, so how is this related to orthogonality? So let's think about that for a second. And one way to see this is that, well, okay, A cross something is a linear operator, it's like on y. Okay, so you can ask, is there some sort of matrix which represents this linear action of A on y via the cross product? All right, so can you represent, right, A cross something as a matrix operation, matrix vector operation, if you will, matrix vector product? Okay, all right. And as it turns out, you can. So what you can do is you can write this in the following way. You can write this as y prime is equal to the following. And I'm going to use subscripts to denote the components of this A vector. Okay, so this is 0 minus A sub 3, and I'm going to suppress the t and y dependence here, okay, just for notational simplicity. All right, so if you look at this, then you should see that this matrix here, right, is skew symmetric. Okay, and of course it's like you know that in the case of orthogonal flows, you know, it's like that skew symmetric matrix plays an important role. So the fact that you have a skew symmetric matrix there is, you know, sort of a hint that maybe it is connected to orthogonal flows in some way, shape, or form. Okay, so I should say that this skew symmetric matrix, right, is related to what is called the hat map. Okay, so this is called the hat map. Okay, so it's basically a map from 3 vectors to sort of this Lie algebra. It's like of, you know, it's like 3 by 3 skew symmetric matrices. So these are the skew symmetric matrices, which is the Lie algebra associated with the rotation group. Okay, so, and it's given by this here, A1, A2, A3 gets mapped to 0 minus A3, A2, A3, 0 minus A1, minus A2, A1, 0. All right, or another way to sort of see this is that the hat map, right, satisfies the following property, right, that x hat y is equal to x cross product y. So maybe there's a bit of notational. Okay, so let me just write x in a slightly more obvious way. All right, so let's write it that way. So x hat times y is x cross y, and you want this to be true for all x and y in R3. Okay, so anyway, this turns out to uniquely define, it's like this map, all right? And again, it's like it identifies sort of 3 vectors with 3 by 3 skew symmetric matrices. All right, so let's see that indeed, you know, it's like a equation like this, where you have a vector is equal to a skew symmetric matrix acting on the sort of time derivative of a vector is equal to a skew symmetric matrix acting on the vector itself, gives you a flow which stays on the 2-sphere, which basically means that the norm or the norm squared of the vector should be a constant. All right, so let's just see that. We can prove that, of course, directly. So let's just see where we go when we do that. Okay. Okay, so let's do this. So you know that y prime is a of y, a times y, where a is a skew-symmetric matrix. So let's look at what happens to 1/2 time rate of change of the norm of y squared, of course, which is just 1/2 the time rate of change of y transpose y. Okay, so you just apply the product rule, so you get 1/2 y prime transpose y plus y transpose y prime, and then you substitute the differential equation. So this gives you 1/2 ay transpose y, right, plus y transpose ay. Okay, and this is equal to 1/2 y transpose ay, y transpose a transpose y plus y transpose ay. Okay, but of course those two are just sort of negatives to each other because a transpose is equal to minus a, right, by skew symmetry. So that's equal to 0. Okay, so that tells you just by directly checking inside the norm of y that you stay on this unit 2 sphere. Okay. Yep. So again, it's like as I sort of alluded to, what you then try to do then is that you write down y, it's like a some rotation matrix. So your ansatz is to write y of t as some rotation matrix, let's say r of t, acting on the initial condition y0, and then you substitute that into the differential equation, and then what you get is that you get an equation, it's like for r, it's like which you want to stay in the rotation matrix. Okay. All right, so so let's see what this looks like. So so if you substitute this into the equation, y prime is equal to ay, right? Then what do you get, right? So, well, first thing you need to do is that you want to differentiate this ansatz, right? So y prime of t is just r prime of t times y0, right? There's, of course, usually a second term, but y0 is a constant, so the time derivative of that vanishes, so you don't have that second term. Okay, so you have that, and of course a depends on y, so what you have is something like r prime at some time times y0 is equal to a, and then now it depends on t in general, and depends on y, right? But y is r of t times y0, so r of t times y0, right? And then you have y, right, which is of course r of t times y0 again. Okay. So technically speaking, it's like if you look at this equation, it's like this equation is satisfied, right, so long as you have something like this, right? R of t is equal to just a of t rt y0 r of t, right? And this is, of course, this would be a skew matrix, r would be a rotation matrix. So this would be the form, it's like which we had, it's like where R is an orthogonal flow, all right? So this is a sufficient condition, if you will, for this thing to be satisfied. And so if you were able to solve this and use this RT, which you get, where R at time 0, I should say R at 0 is the identity, right? Then it would then satisfy the equation which you want, which is that y prime is equal to a of y. right? So if you solve for R, it's like with this orthogonal flow and this initial condition, substitute it into this equation y is equal to R times y0, then that y you get will satisfy y prime is A times y. Okay, so I should say, so caution you to say that this condition in some sense is stronger than this condition. And more or less it has to do with the fact that when you have one way to sort of think about it is that when you have a linear operator acting, it's like on a vector, it's like you don't see the full action of the vector, right? So so there is a sorry, you don't see the full action, it's like of that linear operator, and so if you actually sort of had that acting on on y0, it's like you only see part of that that rotation matrix. And so there are rotation matrices which are not the solution of this differential equation, which would still nevertheless satisfy this equation. And more or less it has to do with the fact that if you have a vector, say y0, and you have a rotation matrix acting on it, then rotation matrices which rotate about that axis, right, don't do anything to the vector y0. So if you test, it's like a rotation matrix on a vector y0, then it doesn't see the part of the rotations which are rotating about the y0 direction. So that's sort of one way to see this. And so that's referred to as what is called the isotropy subgroup. It's like of the action of the rotation matrix on the two-sphere. Okay, so basically what I'm saying is that if you were to just sort of try to solve this equation with the y0 there, then it underdetermines the flow it's like on the orthogonal group. Again, because there is that flexibility, it's like to change the rotation matrix R, it's like by a rotation which rotates in about the y0 direction. Okay, but nevertheless, it's like one possible equation or one possible rotation matrix which does satisfy this, obviously, is the one where you sort of you know, forget about it acting, it's like on y0, and just treat it's like the matrix parts and equate the matrix parts together. Okay, and so this condition gives you a sufficient condition for R, it's like being it's like a solution or generating a solution, it's like of this differential equation which lives in the two-sphere. Okay, so let me just stop there.